Okay, today we're happy to have Lenka come and give us a survey lecture on attention-based models and how to solve them. Thanks, Lenka.
Thanks, Syria, and thanks all for coming or for watching this online since it's being recorded. Um, so I will jump right into it. Okay, that's the so this talk is kind of a walk through these now 7 papers. Is kind of a line of work that continues in my lab. Um, and a priori, like just by judging by the titles of the papers, you would not have maybe guessed that they are kind of really all related with the kind of same underlying methodology that is, related to our usual statistical physics methodology, but kind of with a particular twist in these 7 papers. So this is something that we realized, as you see, the earliest is like 24, so not so long ago. And then this is a list of the kind of all the collaborators on these papers. And I believe before I shared, I saw Emanuele Triani and Fabrizio Boncoralio connecting. I don't know if some few others of the junior collaborators here connected, but they are part also of the collaboration. And Florent, of course, but I don't think he is connecting today. So but before kind of jumping into the papers, I want to give a bit of a general kind of philosophy of what I'm trying to do here. So building theory of deep learning using simplified models. I stole this analogy of the paper airplane from Scott Besma, who was a PhD student of in another group here at EPFL, who kind of said if we want to like compare the AI once understood to the Airbus 380. And now what we are kind of doing in theory now, it's more like studying the paper airplane. And here, this kind of middle picture of how the AI or the brain looks like today. And is this kind of a mess with a lot of ingredients in there where you don't really know like what's necessary and what's not. So of course, like one can attempt to study the ultimate kind of AI and the theory by trying to kind of realize what's unnecessary here and maybe what's missing. But one can also go the other way, kind of starting with the airplane, paper airplane, and kind of hypothesizing that understanding the ultimate AI may be easier than understanding the current system or the brain. So that's kind of the path that I will take. But of course, the other path is also valid. And who knows, right? Probably both of them will bring their fruits. So when it comes then to building these simplified models, I like to think of like what are the essential ingredients, right? When you're cooking your favorite recipe, you have the essential ingredients, and then there are the kind of variants. So this kind of a triangle, I'm showing it in my talks probably since 2018 or so, so since a while, where kind of I like to argue that in order to create a model that has power to predict something and understand something, you do have to model the data and the task. Otherwise, for the worst case data, these learning problems are computationally intractable. So this we know. You would kind of be showing probably something, or likely something void. The neural network architecture should be taken into account because otherwise you are not kind of talking about the current systems, the neural networks, the deep networks, etc. And then, of course, you need to account for the algorithm. If you are not accounting for the computational side, then you may just be talking about, say, approximation theory or approximability, but without taking the algorithm into account, things may be intractable, and hence you're kind of the core of the question, you're putting it aside. And then the fourth ingredient, the large size limit, that always kind of came a bit implicitly in my works, since they all kind of stem from statistical physics. In statistical physics, we always have the thermodynamic limit, but I actually started putting it explicitly as an ingredient because kind of as we know, the scaling is very important, and how actually things scale up. There is not only one way of scaling them up. So actually specifying the large, like which limit are we looking at, is pretty important. So I kind of come from this field of disordered systems, so I can see all these ingredients as a kind of ingredient also in models for mean field spin glasses, where the data, of course, would be the structured disorder. The neural network would be defining the interactions between the degrees of freedom in learning the weights, in physics, the spins. The algorithm and estimator would be defining the energy function and the dynamics that is trying to minimize it or sample it or whatever we want to do with it. The high dimensionality of the system, that would be what we usually kind of abbreviate as mean field in physics. And the large size limit, of course, is the thermodynamic limit. So here we have several different meaningful thermodynamic limits in general. So now, in one slide, kind of the existing exactly solvable models. So in this line of work, for instance, if you look at most of my talks in the past 10 years, there will be about some variants of that. So on the side of the data and task, the kind of models that have been studied are these teacher-student models that these days are called single or multi-index models for how the data and task were created. And the input data may be Gaussian with identity covariance or with more generic covariance or more generic kind of data models. On the side of the architecture, a lot of work has been done on just linear regression, one layer, or generalized linear regression when you have one layer, but with the nonlinear activation function, or fixed features or kernels. Those are kind of related, and this lazy and NTK that would all fall for me in kind of that same class. Or in the case of the multi-index labels, there was a lot of studies of the architectures that only have few hidden units. And on the side of the algorithms and estimators, like either we can aim at the base optimal estimator for that given data structure, and there we study the approximate message passing algorithms, and that's kind of one methodological tool in this line of work. Or we do the more usual empirical risk minimization. We write some loss and we look where it is minimized, either just statistically or by running gradient descent or stochastic gradient descent or their variance. And the kind of high dimensional limit of the regression is commonly the one where the dimension is large, the number of samples is large, maybe proportionally so. So this is just like in one slide, probably summarizing hundreds or several hundreds of existing papers and kind of the core methods behind them. And now I always think it's kind of useful before jumping what I want to tell today is kind of to always say what is the simplest but unsolved case, unsolved in some sense. Okay. So in this case, that's kind of what I highlight here in purple. Already the case where the data is created by a neural network that has width that is proportional to the dimension, and the dimension is large, the width is large, the number of samples is large, in this scaling. And then the network that is learning may have the same architecture, for instance, the same width. So that's a case in which it's kind of the simplest one where we don't have a closed form formula for instance, the performance of the optimal estimator or for the empirical risk minimization. That is when we take this case with a generic activation. And there has been some papers doing kind of numerics and approximations, but overall the exact formula is not yet there. So that's kind of interesting to see how simple can this like still open problem actually be in this business. And now, okay, among the list of my papers, I was kind of giving the case of the quadratic single hidden layer neural nets. So that will be the case that we will be actually looking at. So that's a special case of this like simplest open problem, but in the special case where the activation is quadratic. So the sigma here is quadratic. And here I'm describing the target function. So it's important to distinguish between the function that creates my data. I will be calling it the teacher or the target function. And then the model that is actually learning from those data. So that will be the model. So here in this slide is so far only the target function. So here I will be looking at the class of functions that can be written in this way, with the z being just the scalar product of the inputs times some ground truth value of the weights with which I generate the labels. But then the model that is learning will only see the inputs and outputs, not these weights. And then it may or may not know this width m star. So a star will always be some hidden latent parameter that is not somehow accessible to me, that is just creating the data. Okay. And then the limit in which this is interesting, and you will kind of see that maybe more from the results than a priori, is that when actually the width of this target is scaling proportionally to the dimension. So when the width would be small, that's the previous cases, the multi-index model that is understood. If the width would be large here, then this just becomes all kind of solvable optimally by linear regression. So that would also be an easy limit. But when it is proportional, it's non-trivial. And from the results, we will see that there's the only other kind of non-trivial scaling, that in the limit of kappa small, we will be falling in the previous case. And when kappa is large, we will be also joining the other kind of known case. So this will end up the only kind of non-trivial other scaling limit of the width in this case. And then how the number of samples should scale. So in kind of in what I do, I always pick the scaling where the interesting things are happening. So where one goes from performance that is just like randomly bad to performance that is we are perfectly learning the target function. So that usually happens at some scale of sample complexity, which in this case is quadratic in the dimension. So the choice of the number of samples is given by that. I want to be in that regime where the non-trivial performance is happening. Okay. So now, okay, I will be looking at this two-layer quadratic neural network, but one could also say, and that is kind of to introduce the second kind of chunk in those papers that I showed, one could also say, who cares today about multi-layer perceptrons anyway? Because everything is about transformers. So who cares about this like two-layer neural network? But we will see that technically it's actually very much related. So to explain how it is related, right, what are transformers about? So in most dogs, you see this kind of a picture of what actually transformer is that I have like, I don't understand. If I see this picture, I mean, now I understand what it means. But when I have seen it first, it didn't bring any understanding to me, like just like boxes with colors and keywords written. But it's actually like the main difference between a transformer and a multi-layer perceptron for me kind of boils down to two key differences. So one key difference is that we actually tokenize the data in the transformer. So instead of presenting at the input a d-dimensional vector, as we do to the multi-layer perceptron, we actually present a set of tokens. So a set of length t words or tokens of d-dimensional vectors, where d is the embedding dimension. So that's kind of one difference. And the other difference is then how actually this input matrix, then d times t, is actually transformed by one layer. So, of course, transformer also has the fully connected layers that token-wise do the same as the multi-layer perceptron does, that is just multiplication by a matrix. But then they also have the dot attention layer that kind of mixes the way the tokens and embedding dimensions are transformed. So they involve the multiplication of this matrix that is the data transformed up to some layer that is still t times d. T is the number of tokens, d is the embedding dimension. So we have these three matrices, key, query, and value, that are d times something matrices. The value, if I have a single head, is just d times d matrix. And these Q and query can have like an arbitrary width, arbitrary size, which here I will denote R. Which, okay, in the state of the art transformers is picked in some specific way, but a priori this is a free dimension. We can just choose it as we want in the architecture. And then the signal is transformed in this way where the Q key and value mix kind of along the embedding dimensions. But then the mixing along the token dimensions is done by this attention matrix that is constructed by comparing the key to the query. So this is kind of a twist on how one layer can look like. So if I go back to my kind of picture of the key ingredients, if now I want to study a transformer, I will keep the estimator and algorithm as before, but on the size of the data and task, I need to account for the fact that now my data are sets of tokens. Before they were vectors. And on the side of the architecture, well, I better have this architecture that is actually able to deal with such sequences. And ideally that contains this attention layer. So that's where we will be going. And now, since my inputs are actually matrices of T tokens in D dimensions, if I go to the limit, I already have kind of three choices. What do I take large and what do I take small, right? So it could be that both T and D are large. That's kind of the current state of the art. Both of them, like the embedding dimension is in the order of thousands and the context length T is, well, as large as it can get. So usually much larger than that what the current systems aim at, so large. But we will also be looking actually at the case, so not large context length and small dimension today in this talk, but in this talk I will also be looking at the case where the embedding dimension is large, but the context length is actually of order 1. That will be an interesting set of models for me. And just for fun, in a grant that I wrote recently, I actually even split like the 3 work packages by which of these 3 limits I'm actually taking. So it kind of makes sense to think of how to take the scaling limit. Okay, so that will be these 3 models, or the models in the 3 papers that I'm highlighting here. Let me just tell you, there will be actually 2 classes of models. So let me tell you a little bit about them. So one is what we call this bilinear sequence regression, which is motivated. So the equations that are so far written here, there's just regression and generalized linear regression, just to remind you, right? Because a lot of the kind of deep learning theory before transformers starts with just linear regression, right? A lot of the kind of double descent and learning dynamics and overparameterization, all that can be understood in essentially variants of linear regression. So linear regression surely is a useful model to kind of start with understanding of what's going on. And the question here is, what is the basic model analogous to linear regression or generalized linear regression or perceptron, whatever you call it, but for sequences? So for data that are at the input is a matrix of T tokens. And that's, our suggestion is this bilinear sequence regression, that you take kind of the simplest form that maps a matrix where each sample is a matrix, T times D, to a scalar, for instance, scalar label in the simplest kind of supervised regression cases. And the way you can hence map a matrix into a scalar is just to multiply from the right and from the left by a matrix, and then these maybe not have rank 1, but may have generic rank. So this form would kind of be the analog, or not as simple as the linear regression, but close to it, right? Where this R then will be the width or rank of the model. That will be a new parameter here. So that's one of the models that we will be looking at. And actually, when you think about it, if you heard about this architecture called MLP mixer that was discussed, maybe 4 years ago, so infinity ago in the deep learning kind of time scale, but it's still a pretty interesting architecture that was kind of proposed as an alternative to transformers. What it does, so as transformers, it has this token-wise MLP layer, so that's the same. But then instead of the attention layer that we have in transformers, it actually applies now embedding dimension-wise MLP layer. Okay, so it doesn't have this property of the transformer that the parameters that we are learning are independent of the context length. The kind of MLP that is embedding wise MLP actually has sizes of weights that depend on the context length. But otherwise, in cases where you can easily fix the context length, such as in vision tasks, this actually was performing pretty well, and those papers were showing it. So from that point of view, this bilinear sequence regression is kind of the simplest case of this MLP mixer, where I'm just mixing token-wise once linearly, and then I'm mixing embedding dimension-wise once linearly. Then at the end, I can apply some nonlinearity, and that's directly my output. So the simplest, in the same case as linear regression, is the simplest multi-layer perceptron. The bilinear sequence regression is the simplest MLP mixer. So, okay, but where is the attention? If attention is all you need, here I'm just reminding what I already told you. So that leads me to a second class of models that all will kind of fall in the same analytical framework that we call the attention index model. So here, once again, this is just the way I will be generating the data. So the side of my triangle where I'm thinking of actually what is the task I'm studying and how were the data generated. And here, hence, I'm in the context where I want sequences of tokens. Still, the length of the sequence is d, the embedding dimension t. And I will be thinking of supervised tasks where the labels are generated from the input data using some ground truth, key and query matrix that both here will be the same, and I will call them W star. So that generates the data. The key and query are tight of rank R, why not? And this nonlinearity here can be arbitrary. So for instance, the usual softmax. And in this model, the limit in which I will be able to tell you about its learning behavior is the one where the embedding dimension is going to infinity, but the context length is of order 1, say 5 or 10. Okay. So,
Actually,
okay, so
Lenka
that's kind of,
Lenka had
yeah.
a question. In the usual attention, the input x appears three times, twice in the key query
Right.
dot product and once in the value. And here you're,
Right. So here I'm kind of omitting the value. I mean, this is the simplest way to generate labels,
yeah,
right? So then in the model that is learning, I can or not put the value that may depend.
okay,
Right? In a sense, like I can definitely add the value here. In the papers that we started with, we haven't, but that's not kind of technical hurdle. Then we did not yet explore kind of how much richer the picture becomes if I actually do that, and what kind of interesting behavior we gain by generating the data this way.
okay,
Right. But you could add, so for instance, what we already have done in the paper is that we actually multiply this by X, and instead of observing a T by T matrix, we actually do observe a sequence of T d-dimensional tokens again. So the target task can be a sequence to sequence task. It's actually exactly the same model as we show in the paper, that kind of the sequence to sequence and the sequence to labels is technically, it's not like completely visible, but it's technically becomes the same thing. So that's a little bit like how, as taking the value to be identity, right? That's
yeah,
equivalent to taking the value to be identity. I could take the value to be order 1 of vectors, so of size that is something order 1 times the embedding dimension. Taking it larger would kind of be bringing me back to this unsolved case. So technically, I would not know like how to tackle a value matrix that is kind of extensive times the dimension.
okay. Thanks.
But yeah, all these kind of variants that totally make sense. So this is maybe the simplest to kind of think of the role the attention takes place. I mean, we will see. So far, I didn't say anything. I just made a list of models that we will be studying for the data, not even the ones that are learning.
Hmm.
But now to explain you, so how we are actually analyzing it. Let's go back to the quadratic neural network, and then you kind of need to believe me for a moment that methodologically I will actually tackle all these models in a very much the same way. So here I'm just, so once again the setting of the two-layer neural network with quadratic activation. So now I went back, no sequences, the inputs are vectors. And just to set it a little bit more properly here, I actually center the data so that the mean of the outputs is 0. That's actually useful to then set properly the expectation risk minimization analysis of it. But otherwise, it's, as I stated before, the limit where the width is proportional to the dimension and where the number of samples is quadratic in the dimension, because that's where the interesting change in the test error will be happening. So now what is the estimator? So I will be talking about two estimators, the Bayes optimal estimator for that kind of data. So that's kind of what is not usually done in machine learning. But for me, it's always a nice baseline to first know what is statistically the best kind of achievable performance given this limited amount of data of the type, according to the model that is generating the data. So that I call the Bayes optimal estimator. And to analyze that, I need to write the posterior and compute its marginals. So that could be done with some kind of Monte Carlo or Langevin algorithm. And that's something that we actually are able to analyze and also evaluate with this approximate message passing algorithm. And it's kind of technically simpler for us often to start with this Bayes optimal estimator. So that's another reason why we often kind of start with it. And then the second estimator that is more the one usually looks at is some kind of empirical risk minimization for some natural loss, which in this case will be again a loss that has the form of a two-layer network with a quadratic activation, but not necessarily the same width. So in the Bayes optimal estimator, I assume that I know the width of the target. And in the empirical risk minimization, I will actually, in the paper that we wrote, we will actually assume that the width is larger than the dimension. That's a particular case when there we can be sure that there are no spurious local minimizer, which is something one can actually show in this case kind of geometrically without actually analyzing the learning or other things. Geometrically, when the width is larger than dimension, the kind of learning behavior is still non-trivial, as we will see, but there are no spurious local minimizers. So we will start with that case. So, okay, but I'll start with the Bayes optimal. So how does the analysis look like here? So this is a slide that I could probably apply to 90% of my papers, that there is always kind of the quick path, which relates to some statistical physics method, replica method, or the message passing algorithms. And then there is usually more bumpy, rigorous path to actually show that mathematically. So in this case, we did both. It's in two different papers. One it's at NeurIPS, one the rigorous one is at Colt. So how does that work? Like I could kind of give a tutorial on the replica method. It would take me 5 hours, and on the approximate message passing algorithms, it would take me another 5 hours. So I'll skip that. I will just kind of highlight what is unusual in this case. Okay, so these are just methods that we teach at the master level to the students, and they kind of go their usual way. But what is unusual in this quadratic network with extensive width and quadratic activation? Now, two steps that are unusual. The first one is a type of Gaussian universality. So we can actually, if our target function is this, so here I just wrote again the same target function, I can rewrite it in the following way, right? Where here I'm just not like doing anything, I'm just rewriting things and introducing this Z matrix here that is just summarizing the data, and the S that summarizes a matrix that stems from the weights. Okay, and now I wrote it this way, Z times S star, and I see that that's so. And so the first result is that if I actually, so this Z matrix is not a random Gaussian IID matrix, right? It's a product of two Gaussian IID matrices minus identity. But this Gaussian universality theorem tells us that if we actually replaced it by a Gaussian IID matrix, the asymptotic in the limit that I'm taking, test error, and all the kind of other properties we are interested in, the behavior of the gradient descent and things like that, are actually the same in that limit as if we replace this matrix that is structured by a Gaussian IID matrix. So for this to be true, we really need to be in this limit where the m star, oh, here it should be m star, the target kind of width is, oh, but it doesn't matter here because I'm in the base optimal estimator. So what I'm saying here is that that the width needs to be proportional to the dimension. And in that limit, I can kind of do this change. And when I do this change and realize that all what I want to compute will not depend on it, then I actually end up with a problem that in theory of signal processing is called matrix sensing problem. I have a matrix Z that I'm sensing through some signal S star. And okay, then I will next kind of be talking about that problem. So this type of Gaussian universality was actually, so this type of Gaussian universality, the first paper that I know of that pointed it out is actually, again, technically very related paper about a problem called ellipsoid fitting by Afonso Bandera and Antoine Maillard. And here it's a case of this kind of same Gaussian universality.
Actually, Lenka,
So that's mhm.
that seemed so Z is Wishart and G is Wigner, the spectrum. So you're saying the
Mhm.
spectrum doesn't matter, or at least for what you're computing? Because the two matrices have different spectra, right?
Um, so yeah. I'm not saying that these are actually like these are in no way the same matrices. They are totally distinguishable by many ways. Like if I
Yeah,
present you one and another, right? You have many ways to distinguish one from another. But still, if you actually look at this learning problem and this learning problem, they have for the same S star of the type that we are considering, they have the same test error and train error and say spectrum of this A star at the minimizer. And
I see. That's
so
interesting.
it is a bit surprising because they are not the same matrices, but that's what's happening.
I see.
So I think it's the second paper in my list, that's the cold paper where we actually prove this. So, and for the ellipsoid fitting, this paper also has a proof of that. So that's the first step, this kind of Gaussian universality where we bring this problem to a matrix sensing problem. So now let's look at this matrix sensing problem. So this matrix sensing problem, if S didn't have any structure, but here it has structure, it's again product of two matrices. So if each element of S was kind of an independent variable, then this problem would be linear regression, right? We are just summing, it would just be linear regression in d square dimensions. But we know a lot about linear regression. We have kind of all the kind of methodology to solve generalized linear regression. So that's what we realize here, that this matrix sensing problem actually is a linear regression, but with a very structured prior, with a very structured kind of signal. And so that's all we need to do. We need to go in the literature on the linear regression and look whether this structure of the signal is actually doable, whether we can deal with it. Unfortunately for us, there actually is there's a big literature about kind of linear regression with non-separable priors, and this is just one of these non-separable priors. And from kind of the theory of this approximate message passing algorithm, we know that we will be able to solve this problem analytically and have all the kind of usual replica equations for it if for this prior we are able to write the optimal denoiser, because then that optimal denoiser can be just plugged into the approximate message passing algorithm and it's kind of very modular and that's the way it works. So the question here is, And what is a denoiser? That is, if we had a matrix as star created like that, and we added a Gaussian II denoise to it and created a matrix Y, would we be able to estimate back a star optimally from Y? So that's the matrix denoising problem. And fortunately for us, so that's kind of a sub-problem that we need to solve to be able to proceed with this quadratic network. And fortunately for us, this kind of denoising of products of matrices, the optimal denoising, that's actually something that we did work in the group a few years ago without like realizing that it's related to quadratic neural networks. And it also stands on a work of in the group of Jean-Philippe Bouchot and Mark Potters, where they actually proposed what is the algorithm that is the optimal algorithm for such a problem. And we then kind of showed that indeed this is the optimal algorithm and how it is related to a free energy that is related to this problem, that is related to these kind of spherical integrals that people in high energy physics like to call the HCIZ integrals for Harish Chandraitzikson Zuber. So there is quite a nice kind of technical kind of toolbox behind that. But again, I'm not going to the detail. All that I will say is that this denoising problem is well understood and can be, and the result of that can actually be used to treat this linear regression with structured signal by just plugging this rotational invariant denoiser into the usual AMP, the approximate message passing algorithm. So, and this is kind of how it looks like. So the algorithm that is solving this quadratic, the training of this quadratic neural network optimally, we call it the generalized approximate message passing RIE, sorry, where all that changes with respect to the usual approximate message passing algorithm is the part where we plug in the denoiser. So the denoiser is usually some related to the prior, usually some separable denoiser. And here we just plug the denoiser for this matrix estimation problem. And then the state evolution of this algorithm allows us to derive equations that at the end are incredibly simple for this problem. It's just this equation that the optimal test error is just twice kappa, where kappa was just the width over the dimension. Alpha was the number of samples over the dimension square. And then this number psi that's one needs to solve for by solving this self-consistent equation that again has the alpha here. And the kappa implicitly in what is this mu. And this mu is a spectral density that is just free convolution of the Marchenko-Pastur in a semicircle. So we take these two spectral densities, convolve them. That gives us a spectral density that depends on this parameter mu. That is kind of a signal to noise ratio. That is the width of the semicircle. And then we need to solve this equation for mu and plug the mu in here. So at the end, it's a very kind of simple, elegant equation that we get to get the test error as a function of the number of samples for different parameters kappa that are the width of the target function. And we get a perfect recovery phase transition here at a certain position. And we can now run this algorithm that we wrote and see that indeed, even for finite sizes, it reaches the predicted performance. And this works in the noiseless case and also in the noisy case. And we also see that here there is no, there are phase transitions, but second order like that do not kind of come together with any computational gap. Which is kind of interesting here because if the width of the problem was small, then this is the phase retrieval problem that actually has a computational gap. So it's kind of interesting that as the width grows, the computational gap disappears here, and it's just and it becomes a second order phase transition. So that's something that we were not really expecting, but that's what's happening here. And we can also look at various limits. So for instance, here I rescale the alpha so that actually I kind of illustrate the limit of the small width that converges here exactly to what is known in the phase retrieval with number of hidden units that is of order 1, but large. And that that kind of tells us that what I was highlighting when I was talking about the model, that there is no other kind of non-trivial scaling, that when this kappa goes to zero, we recover the same results as we had when we just had couple hidden units. And when the kappa goes to infinity, that's better visible in this plot, then we actually recover the same result as we would if the signal S star was completely random IID. That's what actually linear regression would do if we ignored the structure in the S star. So that tells us that we kind of covered all the kind of scaling behaviors in this class of target functions. That either we have width that is order one, that's one class of functions that has certain kind of optimal estimator, or it's proportional to dimension, or then it's infinite or much larger than the dimension, and then that's kind of joining. Then that's a case in which linear regression is optimal. So that's not a very interesting case. Okay. So now if we go to from the base optimal estimator to the empirical risk minimization, here the two steps are again the ones that are the unusual ones with respect to kind of some vanilla exercise case of the replica method. The universality works exactly the same here. And in the second step, where I'm actually looking which non-separable denoiser I should plug to the approximate message passing algorithm, here it becomes the following. We actually realize that considering L2 norm on the weights is the same as considering nuclear norm on this matrix S. So nuclear norm is just the sum of the absolute values of the singular values. So nuclear norm is a little bit like the L1 norm that induces actually sparsity on the singular values. So the L2 on the weights of the quadratic networks induces a low rank bias on this matrix S. Okay, so we then this kind of denoiser corresponding to the nuclear norm is again something that can be plugged into approximate message passing algorithm, and we can derive its state evolution, and it again ends up relatively simple, with alpha being again the sample complexity. And now we have two numbers for which we need to solve this delta and epsilon. So small delta is just a parameter for which we are solving. Capital delta is a noise. And again, the equations for which we need to solve involve some spectral density that again is a free convolution, but this time of a bit two different matrices. But otherwise it's like very, very related. And then what we get here is we can get again the learning curves, the train loss, the test loss. Now we are doing empirical risk minimization. So depending on the regularization, we can have interpolation peak. We can look at what happens when things are over-parametrized. The interpolation peak is related to interpolation, obviously, from its name. So we can have a look where that happens, where we actually start to have the network wide enough so that we can actually reach a zero training error when the regularization is small, and compute the corresponding interpolation threshold that has like a nice closed formula that depends on the noise and on the width of the target, but it's a formula. What is kind of maybe more interesting, what I try to illustrate in this picture, is when now we look actually at for instance, the exact recovery threshold. That is how many samples are needed to actually solve this problem. So here, as a function of the target width, the blue curve here is the base optimal threshold. So that's the one that, below statistically it's not possible to solve this problem, and above we have, if we knew where the data, from which model the data came from, we had an estimator to solve it. Now, if we were doing any kind of kernel regression, NTK linear regression, then we actually would not solve the problem unless we are above the interpolation threshold. Whereas the quadratic neural network actually solves the problem thanks to this nuclear norm regularization above the pink line. And we can derive that the slope of the pink line is 3, whereas the slope of the base optimal line is, if I remember well, 1 or a bit smaller. So it's a little bit suboptimal, but crucially, the sample complexity goes to 0 with the target width. So we are actually the simpler is the target function, the fewer we need samples. Whereas if we were solving the same target function with some linear method, we would actually need always quadratically many samples, right? We have so we would never be able to save over the almost trivial method where we just list all the binomials and then run linear regression that has enough samples so that we can recover each coefficient of those binomials. For that, we would need n square samples d square samples or d square over 2 samples. So we would not be able to improve upon that, but already the quadratic null network is doing much better than that. Only needs roughly 3 times more samples that it would optimally need, not d times more samples. So this is a nice separation already in this simple case between, a network that is quadratic, so not as expressive as it could get, but is non-trivially learning features because it's beating all the kernel methods and lazy networks in the lazy regime, etc. We also have access to the spectral density. And since here we are really non-trivially learning the weights, we also have a interesting behavior of the spectral density. So this is really the spectral density of the weight matrix, not any Hessian, just the weight matrix as we converge to it at the end of the learning. And this is so the video is how it evolves as we are giving it more and more samples. So we go through the interpolation peak for the test error if the regularization is small, and then the test error goes to 0, and the sample complexity is composed of this delta function is 0, and then some bulk of outliers, and then some bulk of that corresponds to the noise. So let me show you a little bit more about the spectral density. So this lower panel are actually spectral densities as stem from the model that I'm showing you. And the upper panel, those are actually spectral densities observed empirically in the line of work by Martin and Mahone. So this is one of their early papers in 2018. They have maybe a series of 5 to 10 papers measuring the spectral densities of the state-of-the-art networks. And you see that they we can recover the similar features of these spectra as they have in some, okay, here I forgot what exactly architectures these were. But when I go, when I go to other cases they present in their papers, they also have these cases where the tails become more fat tail, or the outliers are have this tail, that they don't have this Marchenko-Pastur border, but have a tail. So one question that we naturally asked within this class of models is, can we have a version of the model where we would recover these heavy-tailed outliers in the spectrum of the matrices that we are learning? And that led us to a variant of the model where all we are actually changing is you can think of it, we are putting in the target function a second layer weight such that this matrix that combines the second layer weights and the first layer weights has a spectrum that decays as a power law. So if we do that, so that's just changing the data, the task, the target function, then the model that we are learning with is the same, is this quadratic neural network with L2 regularization on the weights of certain width m. Nothing is changing on that side. We just change the target function, and that still falls into our analysis, not completely straightforwardly, in the sense that once we make the spectrum decay as a power law here, we actually need to control the theory at not only infinite dimension, but also at somewhat large but finite dimensions. So this really is, I mean, I see still Cengiz here, that's really similar to what kind of has been done for the ridge regression, right? Where you kind of write the replica equation, state evolution, and then you kind of close your eyes and pretend that it's still true for finite n and g, then somebody else maybe later on proves it, right? So here we are kind of playing the same game, but here in a case that is not the linear regression, right? Here the weights are non-trivially changing. You see the spectrum that is kind of converging to something completely different. So we are kind of deep in feature learning as much as we can. So here is just a numerical test that in the points that the lines is the theory and the points are runs of the gradient descent that indeed show us that that this non-asymptotic state evolution still predicts where the minimizer actually is. So this is something, these are small sizes like dimensions 100, 200, 400, 800. And we are kind of capturing part of the finite size effects that we actually do need to then derive the scaling exponents from it. So we do it and kind of obtain this kind of very rich diagram of different scaling regimes. So we have 1, 2, 3, 4, 6 of them, where some of them are trivial. For instance, if we don't have enough samples. So this is the regularization, this is the sample complexity. For instance, if we really don't have enough samples, then the test error is just a constant. It's just not decay. Okay, or if we have very many samples, then the test error decays, but as something trivial, just maybe 1 over the number of samples. So 2 of these regimes, before we kind of reach enough samples to realize that we can learn like all the components, there's this regime 2 and 4 actually have non-trivial scaling exponents that depend on the Paolo decay of the target spectrum. So there's this regime 2 and regime 4. And now the kind of decays of the test error in these phase diagrams go hand in hand with how actually the spectrum at the fixed point looks like. And that's illustrated here with these cartoons. But now this next slide has the real data. Actually, the colors are the theoretical results, and the blue is just simulations and a histogram from simulations. And here we kind of see that we have some bleeding of things that look like a power law from the Marchenko-Pasteur kind of like bulk. Or so we kind of recover the quantitatively we recover qualitatively we recover the shape of the spectra that one sees in practice. So that's kind of interesting. So now, I should probably, I'm always slower than what I thought. Let me just take a few words about now kind of going back to the sequences and transformers. Like the good thing is that from the theory point of view, nothing. So here I'm just reminding back to sequences. Now this bilinear sequence regression that I already explained what it is, it's this simplest MLP mixer. Now what it becomes from the theory, it actually also has been studied before in the literature, in the works that I'm giving here. But from the point of view of what I'm telling you, it's again like the same model, where it's just in a sense non-symmetric case of this matrix sensing problem that we again solve with the same tricks. Here, the Gaussian universality, we don't even need it because our measurement matrix kind of already is Gaussian, but we need to solve the matrix sensing problem with this structured signal. And again, we get an expression that looks very similar as the ones before, except that again, there is a free convolution of 2 spectral densities, but now they are corresponding to non-symmetric matrices. But in a sense, the reason why we can write these equations is the same as for the quadratic networks. It's kind of structurally the same all. The approximate message passing has exactly the same form as before, where we need to plug this denoiser, but for non-symmetric matrices this time. But again, fortunately, that's like an exercise that we did a couple of years back when we were studying these matrix denoising problems, that we also wrote a paper for the non-symmetric matrices. So that we have, and then the behavior of actually how this model behaves, it's very analogous to the quadratic network because these are essentially the same equations. So we have the same kind of scaling limits, the exact recovery thresholds, the same behavior when we go to the low width limit and all that. And now, going to the last model that actually has the attention in there. So again, I'm reminding how I'm generating the data. It's with this, and I center again the data for technical reasons for which the analysis then gets kind of more reasonable. So for this attention index model, when it comes to the width of this, here I tie the key and query, but the width of the key and query, kind of distinguish again two scaling limits. So there is one if this rank is of order 1, so that we call sequence multi-index models, and we have kind of also a line of work about that, about which I'm not talking, because maybe more interesting case is when the width of the key and query is not so small, that it's maybe maybe 10% of the embedding dimension that would be corresponding more to what people are doing in practice. So there's this what we call attention index model. And when we are looking at that one, we actually realize that it's again technically some form of this, that resembles this quadratic activation two-layer neural network with, the same property that transformed the L2 regularization to the nuclear norm now actually does something very interesting. It transforms the L2 regularization on the key and query matrices into a nuclear norm on their product. A nuclear norm on their product will then make their product low rank. And this is something interesting because in practice, we actually do observe that the trained key and queries, even though we kind of put their rank somewhat large, they often actually end up lower. Because the L2 regularization on them actually induces the nuclear norm on their product. And this we found actually quite interesting because this lets you ask the following kind of almost trivial question, is why in the transformers we are actually training the key and query matrices separately instead of training the components of their product, right? I could have also written the attention in this form where I just multiply the key and query matrices into a matrix M that will be now D by D matrix. And I could just run the gradient descent with respect to the components of this M matrix, rather than the canonical running the gradient descent with respect to components of the key and query matrices, right? And a priori, both should work. You would say, oh, running it on the M makes things even more over-parameterized, so that should not hurt me, that should help. But this is actually not true, because if you were running gradient descent on components of the M, the training would not take advantage of this nuclear norm regularization, and the performance would be actually bad. In a picture that is, again, an analog of the picture that I already showed you, where I showed you all the linear methods and kernel methods will not do better than the yellow line, whereas the quadratic network will do like the orange line. Here we have exact analog of it, but with a different interpretation, which is if we are training key and query separately, then we take advantage of the nuclear norm regularization and recover this perfect recovery threshold that corresponds to the pink line. And if we were training directly their product, we would actually be doing much worse. And in this picture, I kind of illustrate like how much worse the test error would be if we actually trained the unfactorized matrix M. That's the kind of purple line, and the pink line is how well we are doing when we are actually training the key and query separately. So that's something that that maybe was kind of came to the transformer architecture with perhaps different motivation, right? That was somehow thinking about how to memorize things by comparing keys and queries, but it has this kind of, I think, very important role for the implicit bias of the gradient descent to actually train it factorized and not multiplied. And also here we have like similar spectral densities that again correspond to the spectral densities of these key and query matrices that people observe in practice, and like interesting shape interpolation peaks. We can also generalize this to the deep case with some technical caveats on which we are working, but it's not as complicated as the multilayer perceptron. That's kind of curious. So here I just flash back the papers. Now, it's now one should kind of, hopefully, if you will go back to them, you will kind of see this line of work that is kind of building the methodology for the quadratic networks with the base optimal estimator that we start with, prove it rigorously in the second paper. Then we go to the empirical risk minimization that a priori is a little bit more involved, but here it doesn't end up so much more involved. And then we look at the case where we put the Paolo in the spectral density of the signal that allows us to derive the scaling laws in this like deep feature learning regime. And then these three works, one on the bilinear sequence regression, that is kind of the perhaps simplest sequence model, and two on this attention index model, where again, we start with the base optimal kind of understanding of the target function class and continue with analysis of the empirical risk minimization, pointing this importance of the nuclear, of the kind of L2 on the weights, transforming into the nuclear norm on the product of the key and queries. And many things to do that we will probably discuss over the years of the collaboration. And this is just the group in Carges, where hopefully we will bring most of you soon. We are working on it. So that's just so you can look forward to that location.
Great. Thanks, Lenka, for an amazing talk. We're kind of over time. But any questions?
I have a quick question if no one else is. On Lenka, I was quite intrigued by your comment, your observation towards the end about how much better you train if you do the key and weight matrices, key and value matrices separately
Yeah.
rather than multiplying them because of the overparameterization affecting the training. Are there other examples of that? I mean, we know in these deep networks that there are potentially overparameterizations all over the place, preventing effective training. And have you looked at other
Right.
examples of that?
So here it's a bit the other way around, because for me, kind of before we realized that, the kind of canonical story is that the more parameters you have, the better you do, right? The kind of scaling law as a function of the number of parameters. Like, of course, you should not set up the hyperparameters in a completely silly way, but if you do it right, then you actually have the performance going down with the number of parameters. And one would hence want to write models where the more parameters you have, the better the test error is. And when you actually study that with the random features, that's what you see. You kind of go down with the test error towards the kernel limit. But here it's so naively you would think you take this matrix larger. Actually, in practice, the rank of the keys and queries is not so large because you want to save parameters so that it's not too costly in terms of compute time. So people actually do set this rank relatively small. So setting it equal to the embedding dimension, the full rank, would actually have more parameters. So that would cost you on compute, but you would say it should not hurt me in terms of the test error because it's more over parameterized, right? And we show that it actually does hurt you, that in this case, it would have the wrong kind of inductive bias and it would actually hurt you in terms of the test error. Not only the compute, you have more parameters, but also the test error. So that kind of illustrates, right? Overparameterization is good and it's all like at the end overparameterized, but you cannot do it in a completely arbitrary way because some ways would actually hurt. So
Yeah.
that's kind of almost like tautological, but I still find this like a nice illustration, right? Because the reason for it, like, you can say the details of this replica calculations at the end are a bit daunting, like one needs to sit with it. But the argument that I'm doing in here is absolutely elementary, right? It just takes 3 lines to realize that the L2 on the weights, actually, if the function has the form where the weights are multiplied, induce a nuclear norm on the product. And that induces the low rank. And that actually is a good implicit bias. And if you were not doing that, then the test error would be worse.
Yeah. Just some fun
Yeah,
facts.
to me, it's also something that like one should know, and I didn't know it before. Maybe others did not. Sorry, I go.
Actually, Lenka, if you just have a two-layer linear network, right, you could always collapse that to a single-layer linear network. But just looking at the
Yeah,
learning dynamics, that induces a low rank bias if you parameterize it as the
yeah,
product of measures. It's a similar effect.
yeah. It's exactly the same fact. Yeah.
Yeah.
That's exactly because in this matrix sensing,
Yeah.
that's there is actually quite rich literature around this nuclear norm, and
Yeah.
it's for exactly the same reasons as what you're saying.
I see. Okay.
And but then the interesting thing, of course, already in the matrix sensing is that for gradient descent, this is a non-trivial problem, in no way convex, like you don't know actually where you go. And the question is whether kind of the implicit regularization of the gradient descent that is run on a completely unregularized problem is this nuclear norm. There is still like an ongoing discussion around
Yeah,
that.
that's right.
Like here, it's a bit different, right? When we were writing this paper, I was kind of going into the current state of the art and realized that actually all the state of the art models always put a small L2 regularization on the weights. I mean, okay, all I maybe exaggerate, but those, as far as I could kind of understand by going into the publicly available papers, this is actually the case. So this is kind of interesting, right? That maybe if one did not put it, and I never like played with the state of the art systems to do that experiment, maybe that would already just like make it fail. That's an interesting question that I would, if somebody knows the answer, I would be curious. Like I
Yeah.
can play with like small models, right? But the state of the art, I would be curious if that actually just makes everything fail if you remove the L2 regularization.
I mean, they probably scanned that hyperparameter, and yeah, actually some fun facts
Yeah.
like for GPT-3, the key query matrices are 128 by 12,000 or so. So they're going from a 12,000 dimensional space to a 128 dimensional attention space. So
12,000 is the embedding dimension. That's pretty
for
large.
GPT-3, yeah.
Okay, I thought it was okay, 12,000. I was kind of imagining more in the thousands. Okay, 12.
Yeah.
Yeah,
Wait a
okay.
minute, sorry. Do you know what it is for GPT-5?
I don't.
I mean, nobody
Um,
may know. They might not release this, but I'm
yeah,
curious.
maybe.
I presume
Yeah,
it's even larger.
potentially. Yeah. I mean,
Yeah, the 128. That's interesting because in kind of the available models, including the All You Need paper, it's actually the rank is chosen to be the embedding dimension over the number of heads.
exactly. Yeah. So GPT-3,
That's like a choice, and it's a completely arbitrary choice. And then Llama has also 128, I
yeah,
think, if I
exactly.
from my reading of when we were actually writing this paper.
Yeah. So the exact
And
numbers are,
this,
yeah, GPT-3 has 128 attention heads, each one of, sorry, 96 attention heads, each one of which is 128 dimensions, and the product is 12,220. So they just wanted to keep the
okay,
number of dimensions the same, right? These engineering heuristics are kind of interesting.
okay, okay.
Um,
Curious, right? Curious.
yeah.
So yeah,
And anyways, yeah, I think we're kind of out of time. But yeah, thank you so much, Lenka. That was great. Oh, sorry, there's something in the chat. Oh no, okay, yeah. Okay, great. And then we'll see a lot of you next week. Should be fun. Um,
yeah. Thanks,
okay.
thanks for the recording me and Julia who cannot join next week
Oh
over
yeah,
the
there's
last Tuesdays. So